doesn't help if that was like the first match of the season.
Yeah.
And
Because
you're
like
not at your like
he
actual weight.
wrestled like six matches like on Saturday.
And you're not on your actual weight. Not
Yeah.
on your actual weight.
I mean, he wasn't either. We both bumped up. Like we were both like weighted at like 145. So I can't really use that excuse.
So it's like
And
yeah.
probably wrestled 45 today. I'll probably wrestle 38. Well, it's only 41.
Okay, let's see.
It's only like, what, 6 more pounds than I already weighing at. 4 more pounds than 45. Doing.
Alright guys, so the warm-up question is asking you to find the derivative, and then it's asking you to find the value of the function, but also the value of the derivative. So watch out for like those small little marks on the equation.
Wait, does the derivative go after like the f apostrophe x? Okay.
Yeah. So yeah, the warm-up, I'm trying to get you guys to kind of notice some of these little notation things. So the F, like the little like, yeah, apostrophe like so instead, that's asking for the derivative. But then this one's asking for you to put the -4 back into the original function. And then this one's asking you to put the -4 into the derivative. So it's asking for different things without saying a whole lot of words, or any words. So I just want to make sure you guys are used to that notation. And we're going to talk about today a little bit more about like what it means to find the value of the function and then finding the value of the derivative. They both tell us important information. How's Howard's girls?
They have like one really good girl, and they like to put ball pressure on like a lot. But
Do a lot of your volleyball girls, are they just not that good at basketball, or do
they have like
don't play?
there are a couple girls that play basketball too, but not
Yeah.
a good team.
All right. Did we do okay in our warm-up here? So again, derivatives, hopefully, realizing that finding the derivative is hopefully a lot easier this way. So f prime of x in this case is what? It's just 3. So we lose that x, because remember this is like a x to the first power. You take the 1 and multiply it to the 3, and then it becomes x to the 0, and that just cancels. Now f of -4 means we're putting it back into this original function. So we get a -11 here, right? But then f prime of -4, what is the function going to equal there? It's just going to stay as 3. So it equals 3, but there's nowhere to put -4 in, so it just becomes a constant. So it's just 3. That's the value at that point. So kind of a strange one, but at the same time good for us to talk about. All right, so then this g function, what's the derivative? What'd you guys get? 10x plus 2, right? So again, the 5 drops down in front, comes an x to the first. The 2 just, that's all that's left in there. So again, this is going into this one, whereas the other one's going in. So just understanding what they're asking for in each of these. So here, 2 to the second is 4 times 5 is 20, and then plus 4, 24, right? And then g prime of 2. Now we're putting that in here. So this will be 22. So just trying to be comfortable with those different notations and just seeing kind of how that looks. All right, so basically what we're going to talk about today is that when we find the derivative, that value can also be its own function. So, bless you. So there is, it becomes a function as well. Let me write down like the actual math words for it rather than my lame explanation. So kind of our warm-up kind of showed us a little bit. So the derivative function is basically that f prime of x for all x that's in our original function. So this is our derivative. And this is the original function. Now, just like we are with other functions, we're able to graph that, we're able to evaluate it, just like we did in the warm-up question. We're able to do a lot with that function, so it's still just like it's like a new function we just found. If you actually looked in our book, they kind of show you, like with trig, that sine and cosine are actually kind of derivatives of each other, kind of like their graphs. Kind of strange that that works out that way, but we're not testing on that, so I'm not going to show you that because Becca like gets PTSD from trig graphs.
I did so bad on my class. Like, it was awful. Like, genuinely awful. Hashtag retake.
Yeah.
Coming your way this time.
So yeah, I decided to leave the sine graph out.
66. Yeah. Yeah.
That's not Becca.
It's not ideal in this situation. No, that's not. And to top it all off, I'm pretty sure I failed my speech that I had the period before that. So
really? You don't think
yep.
it went well?
Yesterday was the worst day. Yep.
You should practice it.
Yeah.
Probably went though. What?
I had you present the poster yesterday.
Huh?
I presented the poster yesterday. And the poster was literally terrible compared to like Erica looking for me.
Oh, Erica's yeah, that's
good.
good.
She made me. He's like, all right, you need to pick who goes next. And there's literally like 5 minutes left of the class, and she picks me. I was like,
Yeah, probably Erica's
No,
good for
not
anybody. All right, so all right. Again, we kind of did this a little bit yesterday. It's just trying to make sure we understand what all these different values stand for in our situation. So I guess I kind of sounds redundant here. So height is given by, and I just want to remind you, h of t is talking about the height. When we take the derivative of that, the derivative of the height function is the velocity. So understanding that I can take the derivative to find the velocity, so the speed. So, we're gonna find the derivative of this value here, this function, and again, we can do that our shortcut way, and that's then our velocity function. So what is that? 600 minus 32t. And I mentioned yesterday, I think, about the 16t squared. The 16 is talking about gravity. So gravity pushes things towards the ground, that's why we don't float away. And so gravity, like 16, that number, that's not just like an arbitrary number. It's talking about gravity. It's like feet per second that it's pushing us to the ground. So when it asks for the initial velocity, what do you think that means? What's zero?
Like you put it into the equation.
Yeah, so they're saying like time is zero in that case. So the initial, like, so I said our initial, like, what was that, the start. So that's when time is zero. Now, if they're talking about velocity, when t is zero, we're putting it into the equation for velocity. We're not putting it back into, if they wanted to know the height at time of zero, then we put it back into the original. So making sure you're seeing where we're putting things back in. Now, in this case, they tell us the object is propelled upward, so hopefully, I'm guessing the object's on the ground or in someone's hand or something, so it's probably at zero or just like a starting height. But the initial velocity, so like basically what the object is sent out at, yeah, this just goes to zero. So this is 600, and they don't really give us much information. We'll go with feet per second here.
I don't think someone can throw that fast.
No, I'm guessing it's some sort of propelled, maybe like something like some
Like
sort of
a-
rocket, like
Yeah.
firework.
Or maybe like one of those like ball launchers.
Oh yeah.
Like a pitching machine.
Oh yeah.
I think that's still a little fast.
Yeah. I can't like wrap my head around like 600 feet per second, like what that means.
Like
and,
it's hard to like. I think
yeah.
that's too fast to throw.
Yeah, we can convert that to those a little bit for fun. All right, so let's find the height of the object at 6 seconds. Where are we putting that in?
The original.
Yeah, back into the height. So when we're talking about the height of the object at 6 seconds, we have to put it back into h of t. So this goes in as h of 6 versus going into the h prime, which then velocity here, kind of just talking about that right away. So how high is the object after 6 seconds? And then how fast is it going after 6 seconds? So those two things are related, but they're not the same number. I mean, like the speed could change. And technically, as things go up into the air, they're going to be slowing down again because that gravity pushing them back down to the ground. I don't know if this is on its way back up or back down yet. I guess we'll find out. So we have to put 6 into our original equation. So our 600t. Oh, that's really high. It must be some sort of rocket, right?
Yeah.
Because that's 3,024 feet. Is that what you guys got?
Mm-hmm.
Assuming this is not a baseball. Find the velocity of the object at 6 seconds. So again, that goes back into our derivative function. So back into the 600 minus 32t. So it's going in here. Now is this object still going up or is it coming back down? Can you tell?
It's coming back.
Oh.
It's going.
Yeah, it'd be negative if it was coming back down. So it starts going up at a speed of 600 feet per second, and it's still going back up at this, or it's still going up at this point because it's still positive velocity. Once the velocity becomes negative, that's when it's on its way back down. And again, all those details aren't a huge deal, but just kind of thinking about this situation. And the fact that it slows down again makes sense because we're still headed upwards and gravity's impacting that. So it's pushing things back down to the ground. So question, when will the object hit the ground? What am I figuring out here?
When it equals 0.
When what equals 0? Which one?
The velocity.
Velocity, you think?
The height.
What do you think?
The
So you
height.
said, so it's the height. So when will the object hit the ground? We want to know when h of t equals 0. Because when will the height be 0? Because technically, yeah, at some point it's going to stop. So like it's going to be sitting on the ground. But the formula is not going to really help us with that. It's going to, because there's going to be, like, that's the next question. What will the velocity be right before it hits the ground? Obviously, the ground stops it, unless it goes into the ground a little bit. But it, we have to figure out when the height is 0. So we're going back again to this original equation. And how do you guys want to go about solving this? What do you guys do first?
Set one side equals 0
Okay. Now that I've done that, what do I need to do next?
subtract 600
I might. I guess the t squared's throwing me off. I'd probably do something else first.
factor
Yeah, holy cow, Garrett's on
Garrett's
today.
on.
Yeah. I factor a t out.
Man's is
What is
going
happening?
crazy.
This never happened.
It'll still work. I just think it's a little more,
Garrett's going down.
It's actually very easy to
yeah.
with the t there.
And that's essentially what we're gonna do here. But what you're potentially missing, maybe, you have to take the square root. I guess I like this one, because t is 0 is one of our answers. That's because at the start, we were on the ground as well. So it was in like the machine or whatever is propelling it, the launch pad. Then we're also gonna solve this one. And this is what these guys were getting at as well, but I guess I was thinking more this way. This will work as well. The way you guys did it would work as well. So I'm taking 600 minus 16t squared, 16t, and setting that equal to 0. And I'm going to move that, you can either move the 600 or the 16t over. I'd probably move 16t over just to make it positive. And then just divide. Then you don't have to do the square root, but I guess, I mean, not the square root is all that.
You just divide by t.
Oh, yeah, just as long as you remember that t could also equal 0, but yeah. I have my Carl shirt on today.
Nice.
Yeah,
I don't even know when senior night is.
I don't either. I figured I'd just wear it because I had a board again. Get my wear.
Hardly know. My name's Carl.
Well, they did like a boy version of that.
What are you talking about? No.
So 37.5, and then if we're talking about, we're assuming this is seconds. So after 37.5 seconds, it would hit the ground. What's the velocity going to be right before it hits the ground? We're going to figure that one out. Yeah, so we know when it's going to hit the ground. It's 37.5 seconds. So in the velocity equation, we can put the time in there because we want to know what the velocity is. So we're going to do now, put this in to figure out how fast the object is moving right before it hits the ground. And we might have probably just had some sort of weapon of mass destruction or something, I don't know. Let's see, so we have 600 minus 32 times that 37.5. Oh, that's weird. I guess that makes sense. So negative 600 feet per second. So actually,
Oh, so it's the same as it was
yeah,
when it started.
yeah. Right, is that what you guys got?
Yeah.
All right, so flip the page over Sorry, the graph showed up a little bit rough when I copied it. Hopefully it'll be readable. Alright, so the function k is graphed for us there. They want us to estimate the values of the derivative at those particular points. Now, we're just going to have to estimate that. It's going to be kind of hard to tell exactly what this tangent line looks like in each of those spots, but we're going to do our best to just kind of estimate what we think that looks like. Then we're going to take those values and try to draw a graph with them. So, x is -6, x is -3. So it's not like I can figure out the equation of this graph because I don't know how to find an equation of something that looks like that. It's not any type of, like, it's not like it's a parabola or a sine graph or something that I'd be able to find the equation of. So at x is -6, I'm trying to draw a line that's called our tangent line that would just hit that graph at like one spot at -6. And to me that line looks like it would be flat, right? Don't you think? So the slope at that point would be what? What would the slope be if it's
0.
flat? The slope would be 0. So basically we're saying that k prime of -6 would equal 0. So we kind of found a coordinate point for our new function. So we're going to use that to graph that in a second. So that's going to be like a coordinate point. All right, how about -3? This one might be a little tricky. So trying to picture like the slope of the point at that spot.
Is it 1/2?
I don't know. Do you think 1/2 or just -1?
What are they basing this off of?
What's that? So you're trying to, like, so what we're basing it off of is we're trying to draw a line that would only hit that dot at one time, like it wouldn't like, it's kind of just basically the slope of the line at that point. Like, what does that look like? What do you guys think? You think a half?
3. I want undefined, straight up and down.
I would say not straight up and down, because we're trying to follow like the line, but I see what you're saying. Straight up and down would probably be more when we're headed over like this way. It would be straight up and down, would be undefined. I would say something like that. And I don't know if on our homework they have them drawn for you. I'd say, like, to make it easy, I would say that looks like a -1/1. I see what Stone's saying of down 2/1. I'm trying to, you guys have,
Down 1/2.
because that would be here and here. You guys think that's better?
No.
Yeah?
No.
I'll see what our book suggests. The book agrees with me, but whatever.
Well,
I think that's a little bit better. Sorry, I'm going to go with -1. You guys can disagree, but.
What if we accidentally don't write it the right way on the sides?
Well, so I think I'm more looking for, like, did you think the slope was a +4? Like, or did you know, like, that you're following the trend of that line? So, I mean.
But wouldn't that make us get like the actual problem wrong? If we
No, because it's still gonna, like, so if you did a half, I'll show you how little difference that'll make on a graph. It really won't make a big deal. All right, how about -1? What do you think, -1?
0.
I think it's 0 again, right? So like that'd be hitting just like there. So again, here's another point for us. And then at 2. So here. So again, I'm trying to just touch the graph one time there.
Is it like 1?
Yeah, I think +1. It's going uphill now, up 1/1. So we're gonna go to graph this, and again, I wanted to mention, like, cause Stone was worried about his, like, if he said -1/2, like how different that would look, and I'll show you like what a slight difference this will be. So now we're gonna take all those points and put them under our graph, and what that graph will be is it's gonna basically be the derivative of this one. It's our new graph. So -6, 0. 3, 4, 5, 6. -6, 0. -3, -1 is down here. Yours would just be like a half up from that. You know, like, so it'd be so close that like I wouldn't think that, like, it's not like you're down at like -8 or something. Then -1, 0. And then 2, 1. This is not the most interesting graph in the world, I know. But now we want to draw a line, and we want to make sense of like what we think it's going to be doing kind of after maybe. So, so we started at 0. I can't really tell what's happening, but it kind of looks like it's going to start heading down again. I don't know. And that would be a positive graph, so I'm going to kind of draw. But then after 2, is the slope going to get bigger or smaller? Bigger, because it's going uphill, right? So from -2, I'm going to just point, or from 2, I'm just going to point up. Because that's what I'm anticipating to happen. I don't really know what's happening over here, so I didn't draw much of a line.
Looks like a cosine.
Looks like a cosine graph. All right. The last one is just, we're just talking about these two and kind of something that's like kind of math people cool about these two. Now these are two equations you should have seen before. It's the volume of a sphere versus the surface area of a sphere. Those are formulas you guys learned way back when, definitely in geometry, potentially like, you know, middle school even. Why do these look important, like for what we're talking about right now? Does anyone see it? Kind of cutting off my. So when we think all of this is just stuff made up to make us like just totally confused as to what's happening. What's that?
They're multiplying the coefficient by the, I don't know what it's called. 4 over 3 by 3.
Yeah, so this is being, this is being multiplied here. And the 3's will cancel. This will go down by 1. So essentially, SR is the derivative. And again, this is like math people cool. This wouldn't be like, I wouldn't go to like tell my friends at like a Christmas party about this and like expect them to be impressed. Yeah. But to be honest, like this is kind of interesting because like you technically were learning about derivatives back when you learned about volume and surface area. They just didn't call them that because you were like in, you know, 7th grade or something. But technically, so the idea of the volume of a sphere, like how big it is, the surface area is if we pull one of those layers off, that's like the edge all around the outside of that sphere. And so that's the idea, that's just like another visual for what's happening with the derivative. Again, the fact that it's height versus time and then it goes to velocity. Like this isn't just like they're making us learn this because they ran out of math things to talk about. Like this has, you know, impacts in other places. So derivatives are something that are real. It's not just, again, a made up thing that they're doing to make math or life hard on you. So I thought that was kind of interesting. I figured I'd show it to you guys. We're not really doing much with that other than just trying to make another connection to the math we've seen before. So I have homework here for you guys. There's a few questions, like there's like some of the sorry, but it's kind of a wonky assignment because I pulled it from another worksheet. Like it doesn't line up nicely. But. And you guys have time to work. You can work on other stuff if needed. I just realized I've just been recording this whole time.